Well, welcome to the Tech Track, and we have an exciting program, and I'm very happy to start with a little encouragement to the academic world. It's a prize that we have run last year for the first time. We're running here again, and I believe that it will become a tradition of Q2B. The acronym you see there is a bit of a mouthful. It's Applied NISQ Computing. Let me give you a bit of a background here. So I represent USRA. My name is Davide Venturelli. I'm chairing this session. At USRA, what we do is advancing research and education in space science, working mostly with the government, specifically with NASA, but not only. As a matter of fact, this prize exists thanks to the generosity of the Air Force Research Laboratory. This is the second year of the award, as I mentioned, and the way this thing works is that we accept nominations, or even self-nominations, from essentially the pool of papers that are submitted to the archive in 2021, in this case. So up to, I would say, half. Hello? Yeah, because that's when the submission ends. Maybe for the next year, we should allow also the missing period, half November to the end of December, to be included in the submission. We received the feedback on that. And we restrict the pool of candidates to those leading authors that are not affiliated with industry. And this is simply because USRA traditionally has been working with academia and trying to foster academia and government and public research. The theme is applied NISQ. What does it mean? It means that the paper that we award needs to advance the quest for quantum advantage in the NISQ era. So we ask every submission, every nominee that accepts the nomination, also to include a cover letter that explains why this is the case. So it's not only the paper, it's also some sort of elevator pitch of the paper as well. And the prize, well, you're witnessing the prize. I'm going to announce in a few seconds. It's to attend and present a Q2B. This time we also had travel support. And we had a sponsor, AWS, that offered $5,000 in QPU credits. And we also have QCware that has credits for QCware Forge available. And so we really encourage academic and national lab researchers to leverage this opportunity to use cloud computing. So I mentioned this, we are funded by the FRL. Before presenting the speaker that will give a seminar of about 15 minutes, I want to say that the way we categorize applied NISQ computing is inspired by our attempt to organize a bit the archive quant PH category in themes that are more near-term oriented. And I invite those of you that are not part of our subscription list to go on this website and then receive 1 email a month where we create a digest and we put all the paper we see on the archive divided by 10 categories, specifically experiments and architectures divided by the main platform type, and then algorithms that are near-term oriented. And we add a category on benchmarking and software tools for the papers that are also building software that helps accelerate all the algorithmic stack. And we're looking for sponsors to bring this little database to the next level. We have already about 1,000 subscribers, and we have a searchable database. So if you are interested in being part of this little service to the community, please reach out to me. And now it's time for me to discuss who was awarded this year. And we start with an honorable mention. And I want to mention, this time the honorable mention is very special because we had a tight race. Indeed, the two awarded papers had the same score. And we even reached out to our sponsors and see, hey, do you have, you want to weigh in on the evaluations? And the tie was difficult to break. As a matter of fact, we ended up using our submission rule that who submits first is going to break the tie. So I really would like you to congratulate the second paper that was awarded, which is an honorable mention. I think one of the authors is also here. And the winner of the honorable mention of the NISQ QC Award 2021 is Randomizing Multi-Product Formula for Improved Hamiltonian Simulation. Please give an applause to remind ourselves of what an award is. This paper, I invite you to have a look online. This is the archive. Probably will be submitted or published soon. I think Mark Stodner, the second author, is around. You can totally reach out to him to discuss it. The award was for proposing a framework of randomized sampling that could prove useful for quantum simulation beyond product formulas and presenting two novel multi-product algorithms tailored to this framework. And this framework achieves a simulation error that decreases exponentially with circuit depth, which is significantly lower of the depth of other methods, rendering it especially useful for near-term quantum computing. So this is the honorable mention. And I'm going to give the word in a few seconds to the winner, to a representative of the author list of the winner that will present the paper that was awarded this year. And the paper that is awarded this year in its 2021 winner is Behavior of Analog Quantum Algorithms. Please, let's give an applause. I hope this is recorded. The award is for developing a new variational algorithm that seeks to parameterize an approximation of an optimal bang-anneal bang protocol, which outperforms QAOA as well as naive annealing. The ansatz specifically represent a significant advance in understanding near-term design philosophies for quantum annealing and QAOA. And with this, I invite Lucas Kotsiar in representation of the author list to give a brief seminar of about 15 minutes on the paper. And I invite you all to subscribe again to our newsletter and to support this award the next year or in general. So thanks again. And Lucas, the mic is yours. I'm going to prepare your presentation.
Thank you. I had no idea we tied. I'd like to personally congratulate our co-winners as well.
Lucas,
right. I'd like to thank Q2B for the award, and I'd like to also extend the thanks from my co-authors. Unfortunately, the lead author, Lucas Brady, couldn't be here today under short notice, so I will be giving his talk, and I hope I do it justice. Today, I'll be talking about the behavior of analog quantum algorithms. You can find it at this archive listing. And quantum analog algorithms, broadly speaking, fall into three got it. Quantum adiabatic computing, quantum annealing, and QAOA, or the quantum approximation optimization algorithm. In particular, all of these algorithms require the somewhat onerous, frequently onerous optimization over an annealing schedule for the second one, and variational parameters for the last. These last two, though, are particularly promising candidates for near-term devices. So there's a lot of interest in the community to lower this cost. And this is sort of going to be the focus of this talk and the paper. In particular, I'll be pointing out a relationship among all three classes of these algorithms, where in certain differing limits, they all approach the same optimal control curve. This optimal control curve, I will show, has a bang, anneal, bang order. And I will prove that the frequency of the oscillations affects coherent diabatic error cancellation. And I will numerically show that QAOA can often be thought of as a large time step trotterization of this underlying anneal curve, optimal curve. And finally, I'll conclude by showing how these insights can be leveraged to develop an algorithm that outperforms QAOA as well as linear annealing protocols. So let's go the other way. Analog quantum algorithms are generally set up so that you have two Hamiltonians, mixing Hamiltonian, it's frequently called, here denoted by B, which is a simple Hamiltonian with an easy-to-prepare ground state. And this is a Hamiltonian that you can easily prepare on a quantum device and that you know a lot about. And C is a complicated Hamiltonian, which you want to use your control curve to ratchet to on your device. And in particular, you want to learn what its ground state energy is or some related cost function. So the goal is to transfer from the ground state of Hamiltonian B to the ground state of Hamiltonian C. And there are multiple design philosophies for how to do this. The one with the surest formal footing, of course, is quantum adiabatic approximation, which is characterized by varying that control parameter from B to C as slowly as possible. Here you're guaranteed to remain in the ground state, given that you vary this control parameter slower than a polynomial function of the inverse instantaneous band gap during the evolution. If this condition holds, adiabaticity is guaranteed. Unfortunately, for near-term devices, this is a very onerous condition which can't be met, as it far exceeds the coherence timescales of and even in the foreseeable future of all devices. So in practice, people frequently use shorter timescale ramps. And this brings us to a second algorithm of quantum annealing. What happens if you go faster or if you have noise? Many people in this audience perhaps are familiar with this second class because it is one that's been used in industry for quite a while, most notably by D-Wave, where they have an icing Hamiltonian that they can map to max cut problems. However, Google has also dabbled in this, and there's a recent IARPA initiative called the Quantum Enhancement Optimization that aims to improve these algorithms. So because you're no longer in the adiabatic regime where you have guaranteed, you're guaranteed to remain in the ground state, your performance is often poor, but it works often well enough that it's justified and that the trade-off for speed is justified. The end result, though, are rather weird, complicated dynamics frequently, which are difficult to formalize. Recently, the quantum information community has moved to a more formal, perhaps, version of quantum annealing, of the quantum approximate optimization algorithm, which I'll be referring from now on to as QAOA. And here, you add the additional constraint for quantum annealing that your optimization is no longer effectively an infinite set of parameters, but a discrete set of continuous parameters. This allows you to leverage the variational principles guarantee that your system will give you a ground state that is greater than or equal to the true ground state modulo systematic noise, and gives you a better sort of formal handle. And indeed, there's been a lot more frequency of results with QAOA compared to quantum annealing in the recent years, thanks to this added constraint. But generally speaking, you treat your quantum device, your near-term device, as a black box, and you want to vary these variational parameters, gamma and beta, which now, since there's a discrete number, correspond to alternating bangs, affecting alternating bangs on your system of the mixer and problem Hamiltonian. So you no longer have a continuous curve, but a discretized curve. The nice thing about this, and the reason it's so promising for near-term devices, is that you can offload the optimization step onto our current classical computers and do classical optimization to search for the lowest energy by varying these betas and gammas. In other words, finding this optimal discrete curve. So we can ask, what is the optimal form of this discrete curve? And if so, if we find something like that, maybe we can leverage it to increase the rate of this classical optimization. It turns out, as I will show, that frequently the optimal form follows the optimal QAOA curves for lower depth converge to what appears to be a universal curve at higher and higher depth. So here I've plotted QAOA instances for larger and larger depth for the same problem Hamiltonian, where the lighter colors correspond to lower depth and darker colors correspond to longer depth. And you can find this for every Ising Hamiltonian that you run numerically. And basically what you'll see, if you look at the blue curve in particular, which is the discrete control curve U, which is a ratio of the beta and gamma at every pairwise instance, pairwise time, that the darker and darker curves seem to approach a universal dark curve. The question becomes, what is this universal curve? One way to study this universal curve is to look at its continuous analog, and so to go back to quantum annealing. And if you do that, the way to do that is to take a particular QAOA instance. Here I've taken the largest depth, which I think is p equals 12 or 14, which was the darkest blue curve from the previous figure. And here it's plotted in green dots. And you take the total integrated time of this QAOA instance and set that as a constraint of the total time for your quantum annealer. The optimal curve that you'll find, and numerically this is reproduced here, will frequently have the form given by this red curve. I want to point out three things about this red curve. First of all, it ends and begins with a bang and has an intermediate annealing region. Secondly, that it has a frequency that is commensurate with the average pairwise time of the underlying QAOA curve. And thirdly, that it has this oscillatory nature in the middle annealing region. None of these characteristics were imposed upon the annealing solution. The only imposition was fixed total time and giving the same problem Hamiltonian. So this is quite a stark correspondence to see. So let's try to explain these one by one. First, the bang anneal bang. This is actually formally proven by Lucas Brady, the co-author, one of the co-authors, a year ago. If you look for the optimal anneal curve for fixed time, you might think that it will always be a continuous ramp or some sort of continuous curve, but it turns out that you can prove that at the very beginning and at the very end, there will always be a finite length bang. And in the middle, you'll have an annealing region. Okay, so that's explained. Let's move on to the oscillations. I am going backwards. Oscillations. To get a handle on why these oscillations are occurring, you can look numerically at the instantaneous population of the ground state and first excited state for the optimal annealing curve. And what you'll find is, despite being nowhere near the adiabatic limit, the populations in those two states are more or less maintained. There's a bit of oscillation at the same frequency as the underlying optimal control curve, but on average, the ground state population given by the red dotted dashed curve, by the blue dashed curve is maintained near 1, and the first excited population given by the red dashed curve is given in red. And so this gives you insight into maybe what's happening. Could be something like diabatic error cancellation. And indeed, we formally prove this. So if you work in the near adiabatic limit, and where you're allowed to work with 2 levels, and you use the perturbative limit there, you'll find that the rate of leakage between the ground state and first excited state is dictated by the relative phase of those 2 states. When the relative phase is 0, leakage from the ground states, the first excited state is diminished, and when it's pi, it's enhanced. And therefore, any optimization will try to increase the rate of the optimal curve when the rate of leakage is low, and decrease the rate of the optimal curve when the rate of leakage is high. And the rate at which this happens will be commensurate with the rate of precession of the relative phase, which is dictated by the energy gap between the first excited state and the ground state, which is what we find numerically. All right, so finally, why does QAOA seem to follow the same pattern? To try to attempt this question, to answer this question, we tried to deal with QAOA as a large time step trotterization of the underlying optimal annealing curve. And numerically, we find that if we do this, you do see enhancement when the average period, the trotter period, matches, the trotter step matches the average period of the underlying anneal. Unfortunately, these time steps are still too large. Formally, the trotter error is still diverging at a rate proportional to the order of the depth. And so this just gives you insight, it's not a formal proof. We posit in the paper that perhaps you can prove this last order depth error can be canceled by coherent oscillations by taking into account QAOA's additional degree of freedom of being able to vary the period of its bangs around this average period. But more work needs to be done in this direction. So I'd just like to conclude here now by pointing out that you can use the insights that I've been talking about to come up with an algorithm that beats QAOA. What you can do is take a low-depth QAOA, which you can run efficiently on your term device, and use that to seed a higher depth instance by simply appealing to this optimal universal curve and linearly interpolating between the points given by your lower depth QAOA, and then superimposing upon this a sinusoidal oscillation that's commensurate with the average period of the integrated time steps of your alternating bang-bangs from your QAOA. If you do this, you'll have an annealing solution that outperforms the lower depth QAOA with no additional processing cost other than what I just described. And it's also been numerically shown to outperform linear annealing. Again, thank you very much. Congratulations to the our co-winners, and thank you very much for your attendance and attention.